Hello. We will start our exploration of ordinary differential equations today. So, what are ordinary differential equations? That's a natural question. First of all, they are equations. Second, the unknown in such an equation is not a number, but a function. And third, in a differential equation, we expect to see derivatives of this function. Here is an example. It's an equation, definitely, and yx is a function, and that's the unknown in this picture. We can also see some derivatives of this unknown function here, so this definitely is a differential equation. And finally, the word ordinary refers to the fact that these are ordinary derivatives. The function has only one variable, so we are not using partial derivatives, but ordinary derivatives. This type of equation is somewhat different, because when you look at it on the left, you can see some expression, essentially. This is a function here which depends on x. And on the right, we also have a function which depends on x. There is no y here or here, but that's just another function of x. So when we add them with y's and derivatives, this is still a function which depends on x. So x is a working variable, and it's a dummy variable. We could replace x with t, and the meaning would still be the same. Now, in general, we could actually mix up these derivatives in a more complicated way if you want, but this is a special case. It's a fairly popular case where the highest derivative that we can see over here was actually isolated. This is not always possible in mathematics, but in applications this is actually fairly typical, and most people focus on this special case, which is what we did in our definition. So here is a definition of ordinary differential equation. We have the highest derivative isolated, and on the right there is some expression, and the shape of this expression is coded in this function f. And the function f as input has the working variable, and then the function y and all the lower derivatives. The highest derivative is very important because it in a way determines the behavior of solutions and other important parameters. So that's very important, this number 3 here, and we call it the order of the equation. This is an equation of order 3. Before we move on, little interpretation. We can, for instance, imagine that y stands for temperature. Typically, we investigate some quantity, and this quantity changes. Everything changes in nature. Now, the change may depend, for instance, on the location. X could be a location. That's a good name for a location. For instance, I'm interested in temperature, and as I'm walking here, it gets colder a little bit. And then I'm walking back, and it gets warmer again. So temperature depends on location. It would be also fairly natural to let the temperature change depending on time. And then I would put t here. In applications, we usually use suggestive letters. For instance, I'm standing here, and there used to be some temperature here when I came in. I don't know, 30 centigrades. It's really hot this summer. And as I'm standing here, I'm actually warming up this environment, so the temperature goes up. So typically in applications, which is the source of differential equations, they are very important in applications, you study situations, you freeze them, and you look at what influences you can see that influence this quantity. I have some quantity here, and I ask, what is the influence? And if I am able to write down the influence mathematically, then this influence is trying to do some change, which is what we see on the left. So that's a typical interpretation of a differential equation. Before we move on with theory and with those general considerations, let's try a very simple example. Here we go. Imagine that this is the ground, and there is some object hanging in the air over the ground, but obviously, it's not going to be there for long. We know that. It's most likely going to fall. So let's put some mathematics into it. The vertical axis will be the elevation of the object above the ground. And for simplicity, we will allow only vertical movement of this object. And here on the horizontal axis, I put t for time. So this is actually the graph which captures the elevation of this object with respect to time. Okay, here is some differential equation. Let's say this one. What are the influences? You freeze the moment, which is something that is happening a lot in cartoons. Somebody's running, there is a gap or a chasm, and this person comes over this chasm and stops in the air and starts thinking. That's the freezing moment. This person starts thinking, wait, what are the influences? And probably the most prominent influence is the gravity. You noticed gravity before, I'm sure. So here is the gravity. For simplicity, let's ignore other influences like the air resistance. This is really the major one for us, for humans, as we walk here. What is it trying to do? The answer comes from physics. Gravity is trying to accelerate. So it's trying to change the acceleration of the elevation, which is the second derivative of the elevation. We have to be a little bit careful. The gravity pulls down, but the elevation points up, so we have to change the sign. And that's a differential equation. Now you can notice that there is no variable here, no t. This is typical. People are lazy, which is actually not such a bad habit, and what they do, they drop the variable from the function. They just leave it where it is really needed. So when people, mathematicians, write an equation like that, but applied people as well, they would write it in the following way. Y triple prime is y plus y prime over y prime plus x plus e to x. That would be the typical form of such an equation. And we can see it here in our very simple differential equation. This equation, in fact, captures a law of physics. This is the law of gravity. Homogeneous gravitational field, no other influences. This all can be captured in one very simple line. That's the strength of differential equations. They capture laws of physics and other natural laws. That's why they are crucial for many sciences and for engineering. Okay, how do we solve it? This is actually an almost trivial example. That's why I chose it for the start. Okay, I see the second derivative here. It depends on time, essentially, so I can integrate both sides. I integrate on the left, and I get just the derivative, and now I will put the variable there so that we are back on the field of analysis. That's how we write things in analysis, but just temporarily. And I integrate on the right, minus gt plus c. In calculus 1, they kept telling us, when you integrate, when you find antiderivative, you always have to put plus c there. And today we will finally see why it's crucial. Extremely important, plus c. Okay, let's try it again, because it looks like a good move. I integrate again, and I get yt. This is wonderful. What do I get on the right? Minus 1/2 g t squared plus ct plus another constant. Okay, let's say d. I got a function. That's wonderful. I have a differential equation where the unknown is a function, and I obtain the function. That looks very good. Does it make sense? Is it a solution? Good question. What is a solution? Well, we don't need any new theory or any new idea. We know it from elementary school that when you have an equation and you find something which you think is a solution, you can check. You just take this candidate and you put it into the equation. So I have a candidate and I put it into my equation. I should differentiate twice. When I do it, this disappears, 2t comes down, and then I differentiate again. After I substitute, I get this. I get minus g is equal to minus g. Now, notice that this depends on time, in fact, although I do not see it. But there is time hidden in this function, and the fact that it disappeared after differentiation, that's just because this equation is too simple. Okay? But in general, you can see here, if I take some candidate and I put it here, 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 it becomes a function on the left and a function on the right. Now, what does it mean, equality of functions? That's a good question. And the important thing is, we have to specify where we are looking. That's extremely important. Let's see, do I have room for a little note? Here. A little side note. I claim that the function x is the same as the function absolute value of x. Is it true? The answer is yes, on interval 0 infinity. And now it's true. So when I'm comparing two functions, I always have to specify where am I looking at them. That's one of the key notions in analysis or calculus, if you want. And here it works the same. I substituted my function into my equation. And after I did it, I got equality of two functions. And this equality is true everywhere, on the whole real line. So I can put here t belonging to real numbers. And now it is a proper solution. So every time we find a solution to a differential equation, we have to specify the region of validity. Now, why did I put real numbers here? It would be also true if I put t belonging to 1323. That would be still true, but it would be less information. So we always try to put the largest possible set over here. But in fact, not just any set, but I will get to it later. We always try to put an interval. 1323, that's an interval. Real numbers, that's an interval, set of all real numbers. So we always put the interval of validity when we write down the solutions to differential equations. So we actually solved our first differential equation, and we checked by substituting into it that we are really right, that this is a solution. And now let's talk about it. Well, first of all, I can notice that actually I have infinitely many solutions because there are parameters here. That's important. Notice that there are two parameters and the equation is of order 2. This is not an accident. For well-behaved differential equations, there is this deep correspondence between the order of the equation and the number of degrees or the degree of freedom. I have 2 degrees of freedom here. This has an important impact on applications because usually the differential equations that we face, they do not come from mathematics but from some applications. Okay, let's imagine why this is true. Well, this is a law of gravity, and the law of gravity doesn't force a single outcome. For instance, I have 2 pieces of chalk here, and when I let them go, I will get 2 different outcomes because they start at different elevations. Yeah, you can see that. So it is natural that when you have a law of physics, for instance, captured by differential equations, then there is actually infinite many possible outcomes. I could start here and then fall. That's how the elevation develops in time. Or I could start over here at a different time, at a different elevation. I could also take this, what is it? Probably a stone, and instead of just letting go, I could flip it up. And then the outcome would be like that. It goes up, then the gravity wins and pulls it down. This is quite possible. So there are really, really many different outcomes that our differential equation allows for. And our solution actually captures it, which is wonderful. So that's an important thing that we should keep in mind. When we are solving differential equations, we can expect infinitely many solutions. It makes perfect sense. Now, interesting question. Okay, we are usually studying a certain procedure or a certain process. And when we are studying a certain process, we expect just unique outcome. How do we get a unique outcome? The answer is from other information that we have at our disposal. This is a function with 2 parameters, and by the way, when we write solutions like that, we always assume that the parameters can be arbitrary real numbers. We don't have to specify it because it's understood. Everybody knows it. Now you know it too. Okay, if you want to specify a certain situation, you will need 2 pieces of data because we have 2 unknown parameters here in the solution. For instance, I can say, okay, at time t1, the elevation was here, I released it, and at time t2, it hit the ground. So it's 2 pieces of information which we can write down as a formula. Let's see. Y at time t1 is some elevation y1, and y at t2 is some elevation y2. Then we can use this data to actually determine which parameters C and D fit. This is not difficult. We just take this formula and substitute it here. I prefer to show it with a different set of conditions. You will see why in a second. But in this case, I should be also able to do that, and I determine a unique movement, a unique fall of this object. And for instance, it may turn out that we actually threw this object down when we were releasing it, like a basketball. So it went like that. That's a possible movement as well. By the way, these are called boundary conditions, but they are not all that popular in this theory. When we talk about ordinary differential equations, they are much more useful in a slightly different theory, which is called partial differential equations. And one of the reasons is that those boundary conditions may not give you a unique solution. For instance, it may happen that you have an equation, and we will see such an example later, and the set of solutions is just sine functions multiplied by some constant. So let's see that the set of your solutions looks like this. And let's say that you have two boundary conditions. One is here, one is here. You want your solution to be 0 at two specific places. Now, if things are set up well, for instance, if there is 0 here and pi here, then you can have infinitely many solutions of this form. And I don't even have two parameters, I have just one. And still, one parameter, two conditions, that's not enough to force one solution, because there are many solutions like that. I can put anything for C. So these boundary conditions, they are very natural, but they are tricky, and we cannot build a nice theory about them. So I'm not sort of saying that they are useless. They are very useful in some situations. But we are going to build a nice theory here, and for that nice theory, they are not really the best. So what is the best? Well, we are going to look at the following type of situation. Usually, when we study some process, we have a fairly good information what's happening at the time that we started. So there's a specific time t0, let's say. Here is time t0. And we know the original elevation. So y at time t0 should be some elevation y0. And when we are releasing, we actually know how we release it. We know whether we impair some initial velocity to this object. Do we flip it up at a certain velocity, or do we fling it down, or perhaps we just release it like that? So we have this information in applications very often. Complete information about the starting situation. So that's the initial velocity. And again, we have here a formula which has two parameters, and now we have two starting conditions. This is called initial conditions because they initiate the procedure. And when things go really well, based on these initial conditions, we should now determine a unique movement because we know how it started, we know how we've released it. So there are many possible situations if we have just information about the starting elevation. That's quite obvious. But if we also specify the initial velocity, then there is just one outcome. And that's what we should find here. Well, usually the time is actually up to us to determine. When we start some experiment, we usually switch on the timer as well. So typically, the starting time would be 0, and this will make my life easier. Let's see. What happens if I have the following initial conditions? So I have the initial elevation, I have the initial velocity. Well, I substitute my general formula here for y. What do I get? Well, I get minus 1/2 g times 0 squared plus c times 0 plus d is equal to y0. That's the first equation. Let's have a look at the second one. I have to differentiate. I have to take the derivative of y. Well, okay. Y prime is... well, I have it here, actually. I don't have to differentiate. But typically, when we solve a differential equation, we have the solution, some formula for it, and then we can differentiate afterwards. So here's the formula. Minus g times 0 plus c should be the initial velocity. So I just rewrite these equations, keeping in mind that I know the function y, and then I know the derivative as well. And that's a set of two equations with two unknowns, c and d. And it may happen that it's not possible to solve such a system. But in this case, we are able to do that. From the second equation, we see immediately that c is v0. And then we look at the first equation. This term is 0, this term is 0, d is y0. So what we get is a certain solution, and now it's just one specific solution which looks like this. Minus 1/2 g t square plus v naught t plus y naught, t belonging to real numbers. And actually that's a formula which I learned when I was in elementary school and I started with my physics. And they told us if you have an object which is moving in a homogeneous gravity field, then that's the formula for the elevation. And now we see where it came from a general differential equation and from some initial conditions which are taken at time 0, which makes life much easier. Which brings me to the second paragraph in our definition. What is a solution? A solution is some function, okay, which has all the derivatives which are needed. This is also natural, of course, otherwise we cannot substitute. And when we substitute this function, this candidate, into our equation, to the left-hand side, to the right-hand side, we get an equality on some interval I, for all x's from some interval I, which is exactly what is written here. Now notice that there is written open interval. Why open? Well, we want to differentiate this solution, this function y, because we need it in our differential equation. Now we know that if I have a function and I want to differentiate, I need an open set. In this case, an open interval. However, the word open is in brackets. Why? Because differential equations typically come from applications, and there it makes sense to try something slightly different. Let's have a look at it. Where does this data come from? Well, from some experiment. I started it. I take a stone and I release it. Now, does it really make sense to talk about negative times in that case, when I just release a stone and start my timer? And the answer is no. So there is another possibility how to write this solution. And it's this one. It's not exactly proper mathematically, but it makes perfect sense in applications. So people very often do that. Concerning differentiability at time 0, well, we do not really worry about it. You could say something about one-sided differentiability, but it's better just to talk about continuity. So when I write something like that, I mean that the function y is differentiable, but for t strictly larger than 0, and I want continuity at 0. But people in applications then usually do not worry about the mathematical angle as much. Okay, so there are two possible answers. One of them is mathematical, and one of them is practical, so to speak. Okay, that's the first slide. Now we understand what it means when we say a differential equation, which we typically write without this variable, this dummy variable here. We know what to expect when we see a solution. It's some function, it can have parameters in it, or it can be one specific solution which is given by additional data. That's fairly typical. Let's put some definitions and see whether we understand them. Okay, this is not actually a definition, rather it's a convention. When we are solving a differential equation, sometimes we get really lucky and we actually obtain a formula which captures all possible solutions. I didn't talk about it here, but yes, this formula captures all solutions. There is no other type of a solution. So that's very useful if you have something like that, because you have a complete description of the situation. This is the holy grail of differential equations. You get an equation, and from that you extract a formula which captures all the possible behaviors. And this is called a general solution. Very nice, we always try to go for a general solution. And when we find it, we say that we solved this equation analytically. Analytically means we get a formula for the solution. Now, why is this not a definition? Because there are some exceptions. There are exceptional cases when we want to extend this idea of a general solution a little bit farther, but there is no consistent theory about it. You don't find it in books. It's just, well, people use differential equations in applications. They use them in practice, and there are certain ways which are very practical, but they are not worth capturing mathematically. So this is not a definition, because there will be some exceptions. We will see them soon. If using some additional information, we get just one specific solution, then this is called a particular solution. So that's a terminology which is used a lot. Typical way to get a particular solution is exactly this. First, you get a general solution, and then using some extra data, you get a particular solution. Now, I didn't talk about it much, but this is an extremely well-behaved example. This is probably the simplest differential equation you can think of. Other differential equations are much tougher to solve, and sometimes you are lucky if you look at the solution, you work for 2 days, and you get one specific solution. So there are other ways to get a particular solution, not through this general one, but then your situation is much worse because you don't have a general overview of the situation. By the way, I don't know how to solve this one, and I don't think it can be solved analytically. There are no methods known to me, and I didn't find them in any book or anywhere that would actually handle this differential equation. So differential equations are really very, very tough. Anyway, the most popular way to get the particular solution is exactly this one. You specify what's happening at the start. Now, if you get lucky and your differential equation has order n, you get a solution which has n parameters, and then you expect that you will need n conditions to actually specify a certain process, a certain specific particular solution. So this has a name. It's called initial value problem, or sometimes people call it a Cauchy problem. So how does it look like? It has 2 parts. Part 1 is some ordinary differential equation of order n. And again, we have the special form where the highest derivative is isolated. That's how we like it. And you have initial conditions. You have a certain starting time. I'm talking about time because that's a good mental idea, good mental image to have when you are talking about the dummy variable x. But it could also be location, whatever. Okay, so you have the initial time x0, and you know the value of the unknown function. Then you know the derivative, which is the velocity, if you want to see it that way, and so on. Now you need n conditions. If you need n conditions, then the last derivative should be n minus 1. It makes sense. Here we needed 2 conditions, and the last derivative is the first derivative, not the second. So it also works in general. So there are some prescribed values for the function and its derivatives, and there must be n of them, and this constitutes the so-called initial conditions. Now, in general, there is no guarantee that if somebody gives you a differential equation and initial conditions, then you can find a solution. Because in general, the field of differential equations is really very tough. So what we will do, we will look at nicer cases, at nicer types of differential equations, and then it actually usually works like that. You get initial value problem with initial conditions, and you find a solution. This is the perfect way to do things. And in fact, most differential equations coming from applications, they are nice enough to work like that. So that's a typical setup. Enough of theory. Let's have a look at our first example. Okay, so we had our general introduction about differential equations. And now it's time to learn how to solve them. And here we have a nice differential equation. And unlike the previous example, which was kindergarten stuff, this one is actually serious. This is a real, decent, honest differential equation. How can I tell? Well, here we have the highest derivative, so this is a differential equation of order 1 actually. But I can also notice that the unknown function is on the right, and that makes a big difference. Why? If I try the same trick that I did previously, if I integrate each side, I integrate on the left and I get y. So far so good. I put integral on the right and I am in big trouble. I'm integrating the unknown function, and because it's the unknown function, I don't know it, I don't know how to integrate. That's the dead end. So we need a new trick, and I'm going to show you an interesting procedure which is very powerful, but it has some limitations. We will talk about it. And there is actually 2 possible ways to do this procedure. One of them is mathematical, proper, and the other one is practical, and well, you will see. Let's start with the practical one. Step 1. I take this equation and I rewrite it using the Leibniz notation for the derivative. dy over dx is equal to 2x e to negative y. In fact, Leibniz notation for the derivative is very popular in applications. So if this differential equation comes from applications, there is a good chance that it already looks like this. Now, here comes the key part. I look at it and I try to move all the x's to the right and all the y's to the left using the rules of algebra. That's important. I cannot just move things around. I have to use the proper rule for handling equations. What can I do? Well, I can see one x on the left. I don't like it. Actually, it's dx here. Can I somehow move it to the right? The answer is yes. I just multiply both sides of the equation by dx, and it appears here. The usual tricks. Here is y. I don't like it there. Can I move it to the left? The answer is yes. I just divide by it, and you just flip the sign in front of the exponent, and it appears here in the numerator. You can work it out. Simple algebra. What do I get? Well, there is dy here, and in front of it there will be e to y. On the right, 2x times dx. Now, before we go on, this was actually absolutely wrong. Why? Because dy over dx is a picture. It's like a Chinese character which reads derivative. And you cannot take a picture and break it into parts and start moving them around. This is not allowed in calculus, in analysis. So what we got here was actually obtained in an illegal way. And moreover, it doesn't make much sense unless you start talking about total differential, which is a total overkill. We don't want to talk about total differentials. So this whole procedure was really very suspect. Anyway, we can cover up our tracks, our crime, at least partially, by adding integral signs in front of the two sides here. And we get the following thing. Integral e to y dy is equal to integral 2x dx. And now it makes sense. And you can see that what we are actually aiming at is the following. I start with this differential equation, and I try to move all the x's to the right and all the y's to the left. And I have to do it in such a way that I will get something times dy and something times dx. That's the form I want, because then it fits with the integral. Now, normally I would add those integral signs right here, so people would see these two lines, and it would look quite okay. There's no crime happening here. This makes sense mathematically, and how we got there, well, that's our secret. Anyway, integral on the right, an easy one. Let's do it. X squared plus c. What I see here, an easy integral. Let's do it. E to y. Now, where is plus c here? Well, here's the trick. I should put plus c here, but it would be a different c from this one. C1, C2. And then I take C2, I move it here, and I connect those constants. So people from applications, they know that it's just enough to put plus c to the place where you have your x, the dummy variable. Is that it? Well, what am I looking for? I'm looking for the function y. For the unknown function y, I can get it from here if I take logarithm of each side. I have to take logarithm of the complete side. That's another of the rules for handling equalities. I apply logarithm here, and I just get y. And I apply logarithm here to the whole right-hand side, and I get this. Is it a function? Yeah, it's a function. Does it solve my equation? Well, I don't know. So what I do, I take this formula and put it here. I put it here, I played with it a bit, I did it at home, and it worked out. So this is actually a solution. Important part, where is it valid? Well, let's see. I need to make sure that this logarithm actually exists. That's the only trouble I can see here. We should also look at the equation. Is there trouble here? No trouble here. So the only trouble is here. And what do I need? Well, I need that x squared plus c is positive. That's what I need. Now, I talked about solutions on an interval. Yeah, how about solutions on an interval? Well, there's actually two cases. If c is positive, here we go, then x squared plus a positive number is always positive. So here, the solution would be valid on the whole real line. On the other hand, if c is less than or equal to 0, then there are two possibilities. Because we need x squared, and if c is negative, it looks like x squared minus some number is positive. So when you think about it, it goes like that. One possibility is the interval negative infinity, negative square root of c. And the other possibility is square root of c infinity. These are two possible intervals when c is non-negative, non-positive, sorry. How do we choose which one is right? The answer is we cannot choose. The user has to choose based on some other information. Do you remember we talked about initial conditions, how they determine solutions? Well, if you know something more about this process, then you will be able to choose the right interval. Now, what we usually do not actually do all this analysis. Because we are lazy, and because it's actually better to do it later when we have more information. So typically, people actually write their solutions like that. This is, in fact, a general solution, which is perfect, the best thing we can get. The general solution to our equation. And what we put here is usually all the conditions which somehow restrict the validity. If we get lucky, those conditions are so nice that we can actually put a set here, an interval here. And then it's perfect. But if the condition is not so transparent, then we just put it here, and we leave it to the user to work it out. Which is a good arrangement, isn't it? So on a test, if I got an equation like that, and I was asked for a general solution, I would answer like that. That would be my answer on a test. Of course, it's nice to think about possibilities, but I wouldn't put it on a test. Okay, that's one possible question. Find a general solution to your equation. Before we move to a second possible question, let's talk about limitations of this procedure. Well, let's see. We can always rewrite derivative like that. No problem there. Can we separate always? The answer is no. No way. To give just one simple example, dy over dx is equal to x plus y. Now you can spend some time, half an hour, 2 days, a week, playing with this equality, moving things around. You will never be able to get x's on one side, y's on the other side, in such a nice form that the dy and dx are sort of isolated. They are multiplying some other expression. This is simply not possible. So this is the first serious limitation. This procedure is actually called separation, solving differential equations by separation. And in order to be able to do that, your equation must be separable. Separable means that you can separate. So that's rather obvious. Can we somehow recognize it mathematically? The answer is yes. So let's see, we should have a definition here. A differential equation is called separable if the right-hand side is in the form of a product which has some x part in it and y part in it, which is exactly what you see here. So this part would be called gx, and this part would be called hy. So our equation is separable. That's a very special quality, and separable equations are probably the best, because they are easy to handle if you get lucky, which brings me to another limitation. If we get lucky, we have a separable equation, we separate, we attach those integral signs, and then we integrate. And this is the second important place where we have to ask, is there a trouble? Because not every integral can be handled. I mean, you passed your calculus course exam, so you know what I'm talking about. And I'm not just talking about a bad exam or students who are not ready. Sometimes you get integrals that you simply cannot handle analytically. It is known, and you probably know it, that the antiderivative to e to negative x squared exists, but we don't have a formula for it, algebraic formula. So that would stop us right here. So we have to be also a little bit lucky with the integration. And finally, the third possibility for things to go wrong is this. After you integrate, you get two expressions. One of them has x in it, the other y in it. And now we need to isolate y, but obviously this is not always possible. Again, imagine a simple situation. After you integrate, you get y cubed plus y is equal to x plus c. How do you get y from there? Okay, there are formulas. So let me put y to 13. And now, how do you get y out of here? And the answer is you don't. So that's another troublesome situation. There are three situations where things can go wrong, or three opportunities for things to go wrong. But if you get lucky, it should work out. On a test, definitely it should work out. Okay, that's for the limitations of the separation approach. Now, before we get to mathematical justification of separation, let's finish this problem. Let me ask another question. We talked about it earlier. We can have just a differential equation by itself, and then we ask for a general solution. Or we get a differential equation and an initial condition. So here we go. Let's imagine that we get this differential equation and also the initial condition y naught is equal to 1. How would we solve it? Well, if I was given a problem like that, I would first find the general solution. That's the standard approach. I find a general solution and then I look at the initial condition and say, okay, what does it mean? Well, it means that if I put 0 here, I should get 1. That's a very straightforward interpretation. You don't need any tricks for that. That's a common sense. I know y as a function. I have a formula for it, so I just put it here, and I work it out. Logarithm of something should be 1, which means that the something should be e. What is the something? Something. 0 squared plus c, that's c. c should be e. So my solution to this problem, let's call it ya, x, is logarithm x squared plus e, which is valid. I have to be careful. If you forget on a test, there will be definitely a deduction, a serious deduction in points. Okay, e is positive. Here we go. But as I said, usually we do not worry about this general analysis, so normally I would find a general solution, write the condition like that, and then I would say, okay, x squared plus e should be positive. Well, this is true always. I have my solution. That was easy. Let's try it again. Again, we have our differential equation. And this time the initial condition says y at 2 is equal to 0. Okay, I take my general formula and I put 2 for x. And I get logarithm 2 squared plus c is equal to 0. What does it mean? Well, this means that 2 squared plus c, which is actually 4 plus c, should be equal to logarithm of something is 0, so the something must be 1. Of course, I can handle it as any other equation. When I see an equation like that, I would say, okay, can I get rid of logarithm? And the answer is yes. I will apply the exponential function to each side. When I apply the exponential function to the left-hand side as a whole, e to logarithm cancel, and I get 4 plus c on the left. Okay? Now I apply exponential to the right-hand side, to the complete right-hand side. E to 0 is 1. That's the usual trick. Okay. 4 plus c is 1, which means that c is, let's see, negative 3. And I get my solution, yb, for part b. ybx is equal to logarithm x squared minus 3, comma, and now it gets interesting. X belonging to the interval, let's see, here is my condition. My condition reads x squared minus 3 is positive. That's a very simple inequality, and when you think about it, there are two solutions. One of them is the interval square root of 3 infinity, and the other one is the interval negative infinity, negative square root of 3. So there are two candidates for the region of validity. Which one should I take? That's a good question. And the answer is, well, let's have a look at the interpretation. The solution is some function which exists on this interval. There is one solution here. And on this interval, there is some other solution here. In fact, there are infinitely many solutions because there is the C here, so I can, just for the second, imagine that I have really, really many of them, and some of them exist on the whole real line. We saw one over here. So there are infinitely many solutions floating around in space in 2D, and I'm choosing which one? I'm choosing the one which for time 2 yields the value 0. So I look at all these possible solutions, and I'm looking for one which passes through the point 2, 0. That's the right interpretation for the initial condition here. Where is 2? That's a good question. This is the square root of 3. How much is square root of 3? It's about 1.7, I think. So 2 is definitely here. This is where 2 is. So I'm looking for a solution which passes through this point. And quite obviously, it doesn't help me to look here at the interval negative infinity and negative root from 3, because none of the solutions here will pass through this point. So quite naturally, this is the right place for me, the right region of validity. Root of 3, infinity. Which brings me to the question, why do we put intervals? Why don't I put union of these two as the region of validity? And the answer is, well, this is supposed to describe some process. And the fact that the solution does not exist here means that we have no information about what's happening during that time. So you have some solution, the process is going on, and then you lose all the information. And then something else starts again. So it doesn't make really sense to take these two and put them together and say this is one process, because it's not uninterrupted. So every time there is an interruption in our process, for instance in the equation, this may happen, we will see it soon, we stop taking this solution and we start taking another one. We treat it as two different solutions. Okay? Just out of curiosity, I prepared a plot of the two solutions. You can see the initial condition 2, 0 as the dot on the x-axis, and there is the solution passing through it. And then there is the other initial condition, 0, 1. That's the A example. And you have a nice solution existing on the whole real line, which has a very nice shape. So that's how the solutions look like. Anyway, this is the happy end. This is part B, part A, and we saw two typical examples how to handle initial value problems. Equation, initial value. Equation, initial value. Very simple. Okay? So that's the general strategy. When you look at it from above, when you see just the big picture, not the details, when we are solving an initial value problem, then we first focus just on the equation, and we find a general solution, if we get lucky. And then we take the initial condition, and using the formula, we work out the constants, and we have one particular solution. That's the general setup, the general procedure. Okay, that's it for this example. Now let's explore this procedure mathematically. How far can we trust it? That's a good question. Well, to this end, let's try to do the same process, but with a general equation. So what did we do? Well, we rewrote the derivative. No problem there. dy over dx is equal to gx hy. Now, there was this tricky part where we moved the x to the right and hy to the left. And we ended up with something like that. dy over hy is equal to gx dx. And then we attach the integral signs, and now it looks okay. At least at the first glance, nobody can see any crime here, mathematical crime. However, we are trying to be precise now, mathematically precise. We are interested in the procedures, therefore, because the procedures have to be justified. Can we get there in some other way? And the answer is, well, can we do it somehow differently? Let's try this trick. I will keep the derivative on the left. And we have the unknown. I will put it there, because now we are at in the land of analysis. We work with functions. And I will try the separation. So, okay, x is a dummy variable here, so I pretend I don't see it. I see y here, which also has x in it. So I take this and I move it to the left. And I get y prime x divided by hyx is equal to gx. So far, so good. Now I can attach integrals. But when I'm attaching integrals, I also have to attach the differentials. Because I simply take an equation and I differentiate it. Notice that everything which is happening here is happening on some intervals. I didn't know which kind of interval it is here, but I know that it's given by some kind of condition. And the same thing is here. This equality will be studied on some interval I. So these are all equalities of functions which are valid on some interval I. And if I have equality of two functions on interval I can integrate on I. So it makes sense like that. Okay, what next? Well, that's a good question. Here we actually have exactly the form that we want to get. So that was the questionable step. And we actually got it right on the right. So how about the left-hand side? Well, here we go. Notice the following trick. I introduce substitution. Y is a function of x. And how does substitution work? Well, you introduce a new name for it. Let's say, well, I would like to introduce y, but that's not a good idea. So let's say w. Okay, you introduce w. What is dw? dw is the derivative of y times dx. And remarkably enough, this exactly fits with my picture. So what I get here is dw divided by hw. And this is supposed to be integral gx dx. And now I can introduce another substitution. Y is equal to w, but this is a different y. This is no longer my function, but this is just a name for a variable. If you want, you can call it y with a little star. But it's such a small star that we don't see it. Then dy star is dw, and I get integral dy little star divided by hy little star is equal to integral gx dx. And that's exactly this picture. So what we did was actually not quite correct, because y was not a letter. It was a name of a function, but we treated it as a letter here when we were integrating. So from a mathematical point of view, this practical approach has two problems hidden in it. One of them is this separation of dx dy. The other one is handling of y as just a variable. But in fact, the theorem on substitution allows us to get rid of x as a variable here and treat this y as a name, as a new variable. And then everything fits. We find antiderivatives. We can give them names if you want. Antiderivative of 1 over h will be capital H. And here the antiderivative naturally would be capital G plus C. And if we get lucky, we can solve for y. We have to apply the inverse function to h to each side of this equality. On the left, h's disappear, and on the right, we get this. So what we did, we mimicked this procedure in general using mathematical language, proper mathematical language, and proper mathematical justifications. This is y star, and then we change y star for w and w for yx, and we get yx here. So now it's proper mathematically, but we have to be careful again about assumptions. Here the assumption is that the equation looks like that. Another assumption is, well, actually, is there any? Well, important assumption, we should be able to divide by hy. We will talk about it later. Another assumption is that we know the antiderivatives and that we can find inverse function to capital H. Now we are ready. Let's see a theorem. Assume that we have a separable ODE of exactly the right form. Assume that G is continuous on some open interval I. Why is it useful? Well, because if G is continuous, then it makes sense to find antiderivative. It's another question whether we can do it in actual problem. But theoretically, yes, there is an antiderivative if G is continuous. So this is a natural assumption on G. We also assume that H is continuous on some other open interval, and it's not zero on that interval. Why? Because we want to be able to divide. So 1 over H is now a function which exists on this interval J. We denote by capital G the antiderivative of little g, and we know that exists because of the continuity, and also by continuity, because H is continuous and not zero, then 1 over H is continuous. We also have antiderivative to 1 over H. Yeah, that fits. And if H has an inverse function, then we can find a solution. Wonderful. So this is now called a theorem, and it confirms that the procedure was actually correct, assuming that those assumptions are met, which means essentially that we can do separation, integration. Wonderful. We actually proved the theorem here, and the key ingredient was the theorem on substitution. So now we are quite confident that this separation procedure works if the assumptions are met. However, there are little troubles that we have to take care of. This example was chosen to highlight the procedure by itself, but there are some tricky points, and there are examples where we have to be aware of them and know how to handle them. So let's move to another example. Here we go. A differential equation, first order, so far so good. Is it separable? Let's try it by definition. I can see some formula here, an expression which only features x, another expression which only features y, and they're multiplied. So according to the definition, which is not here anymore, this baby is separable. Now we could try to take this function, gx, and play with it according to the theorem. We find capital G. We could try to take hy and play with it according to the theorem, find capital H, and substitute into the formula there, and we have a solution. However, that's not how people do it. Instead, people prefer to go through the separation way that we did before. Why? Well, two reasons. The first reason is that memorizing a procedure is much easier, and also it stays in the memory for longer, and it's less prone to start developing errors and mistakes. Memorizing formulas is much trickier, and it's easy to make a little mistake in a formula that you memorize. So it's much safer, much easier to remember the procedure for separation. That's the first reason. The second reason is that this is a mathematical theorem, so it has to be true, of course. And this forces us to make some assumptions. However, the procedure can actually handle some cases which do not quite fit into this box. So it's more general, more practical. Let's try it. I look at this equation, and I start by writing it as dy over dx is equal to 2x times y minus 1. And now I'm going to separate. So using the rules of algebra, I will try to move all the x's to the right and all the y's to the left. No problem there. So let's see. Dy over y minus 1 should be 2x times dx. Well, it seems that I succeeded. All the y's on the left, all the x's on the right. And if I attach the integral signs, this looks like well-behaved integrals. There is dx at the end with multiplication, dy. Everything is perfect. So that's a very nice example. Okay, let's integrate. On the right, we can see x squared plus c. We saw that one before. On the left, well, in this course, you are supposed to know substitution really very well. So using a simple substitution, this is obviously logarithm of absolute value y minus 1. If you do not see it, then brush up on your substitution. By the way, you can do it like that. A simple shift substitution. And since I'm talking about it, I'm not going to be too big on integration by parts in this course because it's long. It takes time. I don't have time for that. And regarding partial fractions, I'm going to actively avoid them for the same reason, too long. So don't worry about it when it comes to exam, but you do have to know substitution really well, your basic integration techniques. Okay, I have a formula which features y. I will try to extract it from it. Well, there are several things which get in the way. Logarithm gets in the way to y. Can I get rid of it? Yes, I apply exponential to the left and the right-hand side. I have to apply to the whole left-hand side exponential, and I get e to logarithm, they cancel, and I get y minus 1. Now I apply exponential to the whole right-hand side, e to x squared plus c. So far so good. Now the tricky part. I need to get rid of the absolute value. Well, we know that absolute value can be replaced with plus or minus. But we do not know which one. So let's give ourselves a choice. This actually means that I'm multiplying by 1 or by -1 depending on my will, essentially. Okay, on the right, a simple trick. A basic rule for exponential of a summation. Now I take this multiplication, which is implied here, and move it to the right. If you want to see that way, I multiply the whole equation, both sides by plus or by -1. And we get y minus 1 is equal to plus minus e to c times e to x squared. Here we had the first trick. Now we have a second trick. What is c? C is slider. This is an arbitrary real number. We have power over it. As we slide the number c all over the real line, the solutions are changing in 2D. And we are using this slider to adjust our solution to some, let's say, initial condition. We want a solution passing through this point. We move the slider accordingly. As we move the slider c all over the real line, e to c moves all over the positive numbers. So if you want to have some positive number, you can easily set up c to achieve it. If you want 5 here, you use logarithm of 5 for c, and so on. So you can imagine that e to c is actually, again, something which you have control over. It's a number that is free to choose, but it must be positive. You can choose any positive number here and you can achieve it. Then there is plus or minus in front of it. Well, if you have any positive number and you could also have a choice of a sign, you can get pretty much any number, with one exception. You can never get 0. So it makes sense to introduce a new name for this. And we get the formula y minus 1 is equal to d e to x squared. So far so good. And from that we get yx is equal to 1 plus dex squared. Very nice. These two tricks are very useful when it comes to this form of differential equations, those that lead to logarithms. They appear surprisingly often in applications, so it's really a good idea to know these tricks, these procedures. The trick how to get rid of absolute value, because it will always come when you have integral of this form, so you need to know how to get rid of it. And then this trick which simplifies situation for you. Now, the surprising thing is that d is not allowed to be 0. This is very exceptional because we always have this constants d or c ranging throughout real numbers without any restriction. Fortunately, we will get rid of it later, but for now we have to keep this in mind. Now, where is it valid? That's a good question. Well, x can be anything here, x can be anything here. No problem there. Really? How about the procedure? Let's see. No problem with x. How about here? we divide it. That's a problem. This step was valid only under the assumption that y is never 1. Remember, y is a function here. We started to treat it as a letter here, but so far it's just a function. And it's not allowed to be 1, otherwise we are in big trouble. Is this equal to 1 anywhere? And the answer is actually no, thanks to this condition. If d is not 0, then this is never 0, and this whole thing is never 1. So we got lucky, and it sort of fits together. But it leaves an important case open. When we are solving an equation, we can split it into several paths, and we have to explore all of them. So this is a path which deals with the situation when y is never 1. What if y is 1? Well, that's an interesting question. And it has a very simple answer. Let me see. And this is, by the way, related to the fact, which is here, one of the assumptions is that, line 3, h is not equal to 0 on j, on the interval where we play with this second integral here. So that's an important assumption, as you can see now. But it's not always satisfied, which you can see now. And here we have an interesting fact. We have a separable equation, and we assume that there is some y naught which makes h equal to 0. So at a certain value, we cannot do this trick. But then, surprisingly, a constant function which is based on this y naught is actually a solution. It's called stationary solution. So here we have another solution. Yx is equal to 1, x belonging to R is a stationary solution. And it means that there are two paths that we can take. One path which leads to one kind of solution, second path which leads to a second kind of a solution, and then we have to connect them. And in general, they cannot be connected into one formula. It's not possible in general, so then we would have to say something like that. Solution is yx is equal to 1 plus d e to x squared, x real, or yx is equal to 1, x belonging to real numbers. Now, is that a general solution? The answer is, well, it's not one formula. Typically, when people say a general solution, they think one formula. But here, if you look at one formula, notice that d is not allowed to be 0 here, then it does not capture all the solutions. We have to wonder about two cases. And only if we put them together like that, we get a complete information about our solutions. So that's why I didn't put that general solution notion as a definition, rather as a convention, because people would say, yeah, this makes sense to call this a general solution. General solution can be more formulas. Typically, it's one formula with parameters and some exceptional cases. So that's a general picture that people have. Let me make a little sidestep. The name stationary solution is not related to just this process of separation. It's a general notion. Stationary solution means a solution which does not change. And in applications, this is a very interesting situation. Imagine that you have some system that you can play with, and you can describe the workings of the system using a differential equation. If this equation has a constant solution, a stationary solution, then it means that you can set up the system in such a way that it likes that way, and it stays that way, which is very important when you are studying some processes. Let me show just one small situation here. Imagine the following equation. Now, you can easily check that this, okay, I'll make it like that, to avoid trouble with existence. I don't want to have 0 in the denominator. Now there will be never 0 in the denominator. I'm happy, no problem. I look at it and I ask, is there a constant solution? What does it mean, a constant solution? It means a number which, if you put it for y, you will always get derivative equal to 0. It's easy to find constant solutions. You just ask, can I make derivative to 0 by putting some number for y, regardless of x? And in this example, the answer is yes. Yx is equal to 13. X belonging to real numbers. Let's check. For any x, if I take derivative, I get 0, and if I put 13 here, I get 0. Yeah, I have a constant solution. This is a stationary solution. Let's try another one. Y prime is equal to y minus x. Can I find a stationary solution? And the answer is no. Because if I put some value for y, then depending on x, this will be 0 or not. I don't know. So there is no stationary solution. I could make it 0 by somehow tying y to x, but then it's no longer stationary, it's changing. So it wouldn't be a constant solution, okay? So stationary solutions, we will talk about them in the next lecture actually also, are constants. If you put them into the right-hand side, you get 0 for the derivative. So that's a general notion, very useful one. Okay, let's go back to our example. What we see here is a typical situation when separation leads to logarithm. So there are several things that you can expect, and you should know how to handle them. First of all, how to handle the absolute value. Typically, I would actually skip this step, and I would go from here directly here. I would put plus minus on the right-hand side, because I know it can be moved there. It saves time. So students do it as well. After you do this 5 times, you will know your way around it. So instead of absolute value, you put plus or minus to the right. You split your exponential. You introduce a new name. In applications, actually, people prefer to have c for the parameter. So they would put c here. But it would be a different c from this one. Because, well, let's face it. If you write c is equal to plus or minus e to c, that's not something that you can achieve. That's not a very good idea. They would simply replace it somehow. People in applications, they do not worry about mathematics all that much. So if you see it in some book that they pass from here to C, don't worry about it. This is not a substitution, just some renaming. But in my course, I will try to use D so that it's proper. So that's what you can expect. Plus minus trick, E to C plus minus as D trick. And finally, you always have to worry about stationary solutions. And not just in examples with logarithm. Every time you do separation, you have to worry about stationary solutions. Am I dividing by 0? If yes, here comes stationary solution. And then we connect. Generally, this would be the end of the story. That would be the general solution. But in this particular example, we actually get extremely lucky, but we get lucky a lot. Notice that we forbid d to be 0. What happens if I put capital D to be 0? I get 1, which is the special stationary solution. So I can actually connect these into one formula. And that's the happy end. General solution is yx is equal to 1 plus d e to x squared x real. So in the end, and that's what I promised, we got rid of this restriction. I don't have to worry anymore about the values of d. Any real number can be put for d, and that's how we like it. That's how we have it in our general solutions. But as I said, this is not always possible. We will see an example like that when we do some applications. Okay, so that's an important example. You should keep it in mind. And there is a high probability that you will have to use these tricks on the test or in applications. So it's a good idea to know it. Well, there's a little trick. Notice, I said, okay, let's assume that y is never 1, and we get this. And let's assume that y is always 1, and we get this path. What if there is a solution which sometimes is not equal to 1, but then at some time it becomes 1? Could it happen? And the answer is actually not in this particular example, but it could happen in some other examples, and then we are in big trouble. And the situation becomes much more complicated. I will address it in our next lecture. And I will look at a problem like that in practical classes, when we do problems, when we practice solving by separation. And then I will explain what can happen. That's actually fairly interesting. Very often you can do things like gluing different solutions together, which sounds like fun, and it is, but one has to be very careful. Okay, now this was a very important ingredient in solving by separation. This happens a lot, this division by zero problem, stationary solutions. So now we know about it and we are ready to put up an algorithm. So we are not going to go through it now because, I mean, we know it. So this just captures the general procedure that we are following here, including part 2, explore the possibility that hy is 0, leading to possible stationary solutions. Do not forget to explore possible stationary solutions, or you might be missing out on something very important. So that's the algorithm. You can read it at home at your leisure. Look at it, refer to it when you are practicing, but it's so easy that you will just remember it easily. Anyway, if somebody gives us an initial condition, we can always use this formula to determine a particular solution. This part we know. And that could be it for this lecture. But life is more interesting than that. So let's have a look at 2 more examples, because there are some interesting things that you should know, definitely. Okay, at least the next example you should definitely see. Here we go. Here is our 3rd example. And there is something new here. I look at this problem and I notice immediately that y can never be 0. And that's an important consideration which will be having influence all throughout the rest of the solution. It's very important to notice things like that. So actually, every time I see a differential equation, the first thing I do, I look at the left-hand side, I look at the right-hand side, and I ask about restrictions. What does it mean? Well, the solutions exist in the xy plane, obviously. And the fact that y is never 0 means that the solutions cannot cross the x-axis. So there will be some solutions on the top. There will be some solutions down here, probably. But no solution is allowed to cross the x-axis. That's important. Okay, is it separable? Well, we could try it formally. Let's do the separation procedure. dy over dx is equal to x over y, and therefore y dy is equal to x dx. I was able to separate without any trouble. I was multiplying by y, which is not allowed if y is 0, but it's not 0 anyway, so no problem there. I didn't divide by y, so I don't have to worry about the stationary solutions. That's also nice. Well, let's try integration. On the left, 1/2 y square. On the right, 1/2 x squared plus c. Let's make it nicer. Y squared is equal to x squared plus 2c. 2c, what is c? c is an arbitrary number. I have control over it. If I multiply it by 2, again the outcome is an arbitrary number. I can take this and call it something. Properly mathematically, I should be calling it d, but people in applications, they prefer c's, so let's call it a c. Again. But it's a different c. Mathematically, I can imagine that it's c star or something, c tilde or c something, c little dot, invisible dot. Okay? This is a different c from that one, mathematically. Okay. How do I get y? Well, according to theorem that we had before, I wouldn't be able to do that, because y squared is not an invertible function. However, in applications, it works like that. I take square root on the right, I take square root on the left, and I allow myself to choose plus or minus. And I get my solution. That's the beauty of it. It really works like that, with a little bit of care. What's the condition on existence? Well, x squared plus c should be greater than or equal to 0. That's how it works with the square root. No other restriction here. No restriction here. Careful. Y should never be 0. So there are these two conditions, and I have to put them together. If I want y not equal to 0, then I have to forbid x squared plus c to be 0. So from these two, I get x squared plus c is positive. That's the condition. And here I have my general solution, which is actually, again, not one formula, but two. I have a choice, two possibilities. What does it tell me? Well, first of all, depending on C, the solutions exist everywhere, or perhaps only at some places. Let's say x squared minus 1 is positive, two possible solutions. So I can imagine there are some solutions which exist like that, and some solutions which exist like that. That's the first observation. None of them is allowed to cross the x-axis. The second observation is that I have a choice of signs. So for every solution which is positive, I get a solution which is negative and which is symmetric. So, okay. Of course, these are not the actual solutions. If I really wanted, I could perhaps try to figure out how they actually look like, but it's not worth it. Typically, when you are solving an equation and you get somewhere here, you don't really know the shapes of the graphs. But you should have some general idea of what's happening. So this is what's happening. The x-axis is forbidden. There are some solutions floating above, some solutions floating down here. That's the situation. Some of them may be interrupted. This may happen. Perhaps like that even. We will see. Okay. I just solved the problem called find a general solution of this equation. Yeah, I get my general solution. And a new trick, plus minus as a cure for y squared. Very useful, sometimes happens. Okay, let's play with some initial conditions. And to make life more interesting, let's try 4 of them, I guess. Let's see. Here we have 4 initial conditions, but they are not together. Each of them is a separate problem. We always imagine that it's actually an initial value problem consisting of this differential equation and one initial condition. So let's try the first one. If I want to satisfy this initial condition, I just look at my general solution and I substitute for y. So this means that plus or minus square root, what is x? X is 1. 1 squared plus c should be 2. And that's a simple equation to solve for c. I square both sides, and I get 1 plus c is equal to 4, which means that c is equal to 3. c is 3. So my solution, ya x, is square root x squared plus 3. And there are 2 things we have to worry about now. Let's first handle the easier one. Region of validity. Well, x squared plus 3 is supposed to be positive. That's our condition that we came up with. And this is true always. So we have a solution which is valid on the whole real line. But then there is the choice of the sign, plus or minus. And we have to go back to the basic idea of an initial condition. Initial condition, it means we are looking for a solution which passes through point 1, 2. When time is 1, let's say here, the value should be 2, somewhere here. We are looking for a solution which passes through a point up here, and quite obviously we will never reach that point if we take the version with minus square root. These guys are hanging out down here, below the x-axis. So quite naturally, we are choosing the plus version. Because then the outcome will be 2 if we put 1 there. It checks. 1 squared plus 3 square root with plus sign is 2. Okay? So that's actually fairly simple. Sometimes we have just one selection. When we have several intervals to choose from, this can happen. And then we look at the initial time, which will pinpoint the right interval. Sometimes we have a choice of values, and then we have to look at the value, and that one we'll choose. Common sense. Okay, that's the A problem. Let's have a look at the B problem. Okay, plus or minus square root. Time is 5 squared plus c should be negative 3. Okay, again I square, and I get 25 plus c should be 9. So it seems to me that C is, I subtract negative 16. Let's see. YB x is square root, and again, let's leave this for later. X squared minus 16, x belonging to, and let's think. Okay, x squared minus 16 should be positive. This means two possibilities. Interval negative infinity, negative 4, and 4 infinity. Which one of them do I want? Well, I want the interval which allows me to specify time 5. That's the initial time. So for the initial time 5, this right interval will work, but not the left one. So that's the mathematical answer. And I talked about it earlier. It might make sense in applications to instead put t greater than or equal to 5, or x rather, x. X greater than or equal to 5. But it's just a side note for applied people. Mathematically, I prefer the largest possible interval, which is this one. How about the sign? Let's see. My aim is to pass through the value negative 3. Can I get through there using the square root? The answer is no. I have to put negative sign here. That was easy, wasn't it? Okay, let's move on. YC x is equal to. Okay, what's my condition? I put negative 5 for time. I add c, and I want the answer 4. So if I square, I get 25 plus c should be 16. So c should be negative 9. And again, there are two intervals to choose from. One interval is negative infinity, negative 3, and the other one is 3 infinity. Which one is the right one? Well, I want my initial time to be negative 5, which happens to lie in the left interval. This one is gone, and this one is the right one. Negative infinity, negative 3. How about the sign in front of the square root? The value should be 4, which is plus. Okay? Let's check. Negative 5 squared is 25, minus 9 is 16, square root is 4. Yeah, works out. Okay, the last one. Y1 is equal to 0. Square root of 1 squared plus c should be 0, which means that if, plus minus. If I square, I get that 1 plus c is 0, and c is equal to negative 1. Wherein lies the problem? I get square root x squared minus 1 as the solution, plus or minus. Well, plus or minus. I have 0 here. What's more important? The condition on existence. X squared minus 1 should be positive. X squared minus 1 should be positive. This means that x should be greater than 1, taking into account my choices. But number 1 does not lie there. What's the other choice? The other choice is that x is less than negative 1. The interval negative infinity, negative 1, 1 infinity. These are the two choices, but none of them contains 1. How come? Where's the problem? Well, here it is. Y is not allowed to be 0. I didn't have to do any calculations just by looking at the equation. Y should never be 0. Y is 0, impossible. No solution. That's the correct answer for part D. And that's it. So in this example, we saw, well, a new trick with plus or minus square root. And we practiced choosing the right interval and also choosing the right sign. And they are both very natural if you have this idea of how solutions behave. For instance, here we are looking for a solution which passes through point 5, negative 3. 5, negative 3 is somewhere here. So we have to choose the interval which is on the right, not on the left. And we have to choose the negative version of the square root. It makes perfect sense if you just imagine the picture. Okay, let's have a look at some pictures. What we see here is the 3 existing solutions. And again, I also outlined using small circles the initial values. So there is initial value y1 is equal to 2. That's the little circle in the upper right quadrant. And there is a solution passing through it which exists everywhere. That's the nice curve. Then there are those two solutions which exist only on some subintervals. No surprise there. And then there is the initial condition y1 is equal to 0. And there's no solution. I didn't draw there because, well, it does not exist. An interesting thing. Notice that there are actually two conditions coming into play. One of them is forced by the square root, and one of them comes from the equation. Now, the square root condition, that one is embedded in the problem. I cannot do anything about it. But this condition was actually caused by me, because I chose to write the equation in this way. Good question. What happens if I decide to write the equation like that? In that case, all the solution process will be exactly the same. So I end up with the same formula, but now the restriction will be only coming from the square root, which means there will be equality here allowed. Does it make any difference here? No. This exists everywhere. Nice. But here now, I would be tempted to actually include number 4 in the interval. And well, properly, mathematically, we should just work with open intervals. So I would probably keep it like that. But in applications, it might make sense to include 4. And we have this interpretation about continuity at those closed endpoints. So this could actually make sense to put closed interval here and closed interval here if the equation comes like that. The largest difference comes here, because if I allow y to be 0, then I no longer am forced to take open intervals here. So for this equality, this equation, with this initial condition, I suddenly solve the problem, find c, and I end up with a formula like that. Yx is equal to plus or minus square root x squared minus 1. And there are two candidates, and I'm picking the one which includes 1, which is exactly the interval 1 infinity. Now, what is remarkable about this solution is that I'm not able to decide between plus or minus, because both variations or both versions actually yield value 0 when I put 1 for time or for x. So there's actually two possible solutions to one initial value problem, and it's very special. Here is a picture of what happens if I write the equation in this new way. We have these 3 original solutions, which we have here, but now there are 2 new solutions starting at 1, 0. And this is very unusual, especially in natural sciences, because usually when you have some law, like the law of gravity, you definitely do not expect objects to choose how to behave. There is a choice. Very strange. Differential equations that behave in this way, they are usually quite troublesome. And again, I will talk about this in the next lecture when we talk about uniqueness of solution. Uniqueness, that's what we have here, just one solution. But here we don't have uniqueness, and that's a clear warning sign that there is something really interesting going on. It's interesting, but from a mathematical point of view, it's troublesome. But it's interesting. It's nice. Typically, you don't meet examples like that. Most differential equations that you meet, especially if they come from applications, they are well behaved. They don't do things like that, but they can. Especially if they are dreamed up by mathematicians who are devious and evil, you know that. If I were choosing which version to put on a test, I would probably prefer this one to force you to work. You would have to worry about this condition and to avoid this trouble because, yeah, but perhaps not, you never know. Yeah, this could happen. This concludes our survey of, let's say, popular problems that we should know how to handle. In the previous example, we had this logarithm absolute value plus minus trick. Here we have another plus minus trick an interesting situation with a non-unique solution. And again, that could wrap up this lecture, but I will add one more problem just to explore some interesting situations. See you. So, the last example for today's lecture. I look at the equation, and my first question is, do I see any restriction? And the answer is yes, I do. Actually, I see two restrictions. X should never be 0. Y should never be 0. How do I imagine this restriction? Well, here is my xy world where the solutions live, and they are not allowed to cross the y-axis, and they are not allowed to cross the x-axis. So they live in the quadrants. They never pass through those axes at all. So I already have some basic idea what to expect. Okay, let's try separation. Let's see. 3y over x dy over dx should be 2 over y. Okay, I throw all the y's to the left, all the x's to the right. Does it work nicely? 3y squared dy is 2x dx. Okay, I separate it, good. I integrate. By the way, when you see constants like that in a given equation, it's usually a good idea to leave them where they are. Why? Because the teacher put them there to make your life easier, so that he has an easier time to read your solutions, okay? Let's see, 3y squared, I integrate, y cubed. Nice, see? That's what these constants are for. 2x, I integrate. Here we go. Now the cubic power is invertible, no problem there. Yx is equal to the cubic root of x squared plus c. Now, what are the restrictions? Very important. Well, first of all, x should never be 0. The second source of trouble comes from y not being allowed to be 0. So x squared plus c should also never be 0. Can I connect them somehow reasonably? And the answer is no. No, these cannot be connected. Okay, is there anything else? Cubic root exists everywhere. Square power everywhere. No problem here, no problem here, no problem here. I didn't divide by y, so no stationary solution. Yeah, that's it. Here is my general solution. Was it simple? Definitely. Let's have some fun with initial conditions. Okay, here we go. y1 is equal to 2. So, 1 squared plus c cubic root should be equal to 2. Which means that if I take the cubic power on the left and on the right, 1 plus c should be 8. And therefore c is 7. Okay, let's see what it means. It means that the solution yax is the cubic root of x squared plus 7. Now, what are the conditions? Good question. Well, x is not allowed to be 0, and x squared plus c is not allowed to be 0. But this will never happen. So the only condition is that x is not 0. That's what we have to worry about. This gives us two possible intervals. Negative infinity 0 and 0 infinity. Which one of them is right? The right one, because we need time 1. Time equal to 1 lies here. And that's the answer for the first problem. Okay, let's move to the second one. Time is 1. 1 squared plus c cubic root should be negative 2. We take the cubic power. 1 plus c is negative 8, so c is negative 9. And therefore the solution ybx is the cubic root of x squared minus 9. What are the restrictions? Good question. X should not be 0, but also x squared minus 9 should not be 0. So x is not plus or minus 3. Okay, so what are the options? There are 3 values which are forbidden. 0, 3, negative 3. It looks like that. 3, negative 3, 0. So there are 4 intervals to choose from. 1, 2, 3, 4. Which one do I want? I want the interval which has 1 in it. 1 is over here. That's the right interval. So x belongs to 0, 3. That's the condition for my second solution. So far, so good. Time is negative 1. We square it. We add c, take the cubic root, and we want this to be 1. So I take the cubic power. 1 plus c is 1. C is 0. Okay, that's nice. yc, the solution for the c case, is the cubic root of x squared. That's remarkably cute. Okay, what are the conditions? X squared should not be 0, and x should not be 0. Well, x should not be 0, obviously. So again, we have 2 intervals to choose from, and we want the one which has negative 1 in it. Well, there's not much choice. Negative infinity, negative 1. Okay, so far so good. 6 squared plus c, and the cubic root should be 3. Interesting. 6 squared is usually 36. Plus c should be 3 squared, 27. Okay, how much is c? The answer is c is negative 9. So the solution for part D is the cubic root of x squared minus 9. What are the conditions? Well, this looks remarkably similar to the part B. The same formula and therefore the same conditions. The same picture coming here. Negative 3, 0, 3. But a different initial time. Time is 6. 6 is over here. So x belongs to 3 infinity. This is a little pedagogical moment. It looks like these 2 solutions are the same, but they are not. Why? Because they live at different places at different times. So these are 2 separate processes. And that's it. Let's have a look at the picture. Wakey, wakey. Here we go. So what do we see? Okay, case 1, 1 and 2, 1, 2. That's the upper curve which goes to the right, slightly curving upwards. It's a nice solution. It was interrupted when it reached the y-axis. Why? Because there is the condition x not equal to 0. That one is forbidding the y-axis. Okay, second solution. 1 is equal to negative 2. That's the bottom, well, it's a pit, bottom of the pit, or of a bag. Bag's end. Okay, there is a solution going through there, and it's actually, the endpoints are determined by 2 conditions. We are not allowed to cross any of the axes. So it's just this little tiny curve which claims to be reddish. Okay. Then, part C. That's the curve that we can see on the left. Goes through negative 1, 1. And it's actually x to 2/3. We could write it as one formula. And finally, the fourth solution continues where the bottom one stopped, because it's actually the same formula, but they're interrupted when they cross the x-axis. That's why it's a different solution, the green curve. Okay? So we see 1, 2, 3, 4 different solutions in this picture. I hope this all made sense and it was easy. After the previous problems, nothing new here. But now we are going to play a little bit. I look at this equation and I say, okay, what if I ask for the equation 3y, y prime is equal to 2x over y. It's exactly the same equation, but now this condition is no longer valid. X can be 0 now. So the only restriction is that y is not 0. And my question is, will there be any change in the picture? Well, let's see. Part A. X squared plus 7 cubic root. We had one condition, x not being equal to 0, but this no longer applies. We only ask about y not being 0. So we want this to be non-zero, which is always. So there is a change. Okay. 3 conditions here. The one with number 3 comes from the condition that y should never be 0, that the function by itself should never be 0. So this condition is still valid, but the 0 condition is no longer there. So we have just 2 dividing points, 3 and -3. And we are living here at time equal to 1. So this whole interval should work. Interval now is -3, 3. Okay. Y should never be 0, which actually means that x should not be 0 in this case. Here both conditions coincide. We didn't really save anything. Still the same story. Negative infinity, -1. And find, oops, x belonging to. And finally here, the condition that x is not 0 is dropped, but we still don't want this function, the value, to be 0. So 3 and -3, they are still forbidden. And since we are choosing the right interval, the condition about 0 doesn't make any difference. We ignored it before, we ignore it now. So this one stays the same. So 2 conditions remaining as they were, and 2 conditions becoming less strong. We have larger intervals. How does it translate graphically? Here there were 2 restrictions. The x-axis was forbidden, y-axis was forbidden. Now only the x-axis is forbidden. So any solution which stops at the y-axis is now allowed to continue. Let's see. Here we go. So we can see that the upper curve got prolonged, and now it exists everywhere. And this little pit down there, this little depression, is actually now existing on a symmetric interval -3, 3. Very nice. Okay. I think you can guess my next and last question. What if the equation is given like that? Now there are no restrictions at all. Let's see. No problem with x, no problem with y. And we look here, and we see no problem with the cubic root. Cubic root exists for all numbers. No problem here. It seems that there are no problems at all. So one would be tempted to actually assume that all the solutions would be actually valid everywhere. In particular, these 2 would now merge, because this solution would exist everywhere, a nice curve, and this solution would exist everywhere, a nice curve. So it would be the same solution, but given by 2 distinct initial conditions. However, let's have a look at it. Unfortunately, it's not true. Why? Well, when you look at it, this C solution, x to power 2 over 3, it would get extended, but notice how it connects. It connects in this way. And we learned in calculus that when you have a function like that, there is no derivative here. But how can you have a solution without a derivative if the derivative is in the equation? That's a problem. Let's have a look at the derivative. If I differentiate the formula there, I have to use, well, okay, let me write it first like that. It's x squared plus c to 1/3. So we differentiate, 1/3 comes down. Then we decrease the exponent by 1, which becomes negative. So it becomes like that. and by the chain rule we pass inside. That's the derivative. Where does it exist? The answer is the condition x squared plus c is not 0 actually describes the existence of the derivative. And because we do need the derivative, we still have to worry about this condition. We can never get rid of it, even though it's not visible here, and it's not visible here. So in fact, when we are looking for the solutions, for the region of validity, we should be looking at the equation. We should be looking at the solution, at the general formula, and we should be looking at the formula for the derivative, and then we can be sure that we have the correct answer. So in fact, these two equations, they have the same solutions, because this condition is hidden in the existence of the derivative. Devious, I would even call it mean. I mean, this is really bad, because most people would miss out on this condition. I would actually miss out on it too, most likely, if I weren't ready for it. So some examples, some problems are really tricky, treacherous, I would even say, but fortunately they are extremely rare. I actually had to work on this one to create it in such a way that it would cause trouble. Typically, the cubic root in the solution causes trouble like that. And otherwise, things are pretty nice, okay. Well, what did I do here? I was supposed to connect like that. Okay? So that's the end of this example. It shows that there are some finer points where one has to be careful. But fortunately, they are quite rare. So if you forget, there is a very high probability that you will be okay anyway, but you shouldn't forget, of course. We have to be careful with the solutions. We have to be careful with the mathematics. Fortunately, people in applications, they usually meet equations which come from nature. And Mother Nature is usually very nice to us and doesn't cause troubles. Okay, that's it for the lecture. And in the next lecture, we will address the problem of whether we can extract some information out of equations that we actually cannot solve, which is a lot of them, probably the majority of them. We have to be really lucky to be able to solve them. Okay, see you then.